So my video is not getting turned on. Okay, from here I have to switch it off. Good. Okay. So maybe I'll begin with the number theory version of the question. Okay, and that will be as follows. So we know that given this a bigger than b, two integers, okay, a and b, let's say just natural numbers. Yeah. If you divide a by b, so you divide, we all know, right? You get a quotient and a remainder. And we know that the remainder is less than what you divide, right? Strictly less than what you divide. And it could be 0. So do all of us know this? Someone who doesn't know this, that this can be done for any two integers? Okay. Yes, I'm just saying that given any two integers, right, you can divide one by the other and you get a quotient and a remainder, right? So this fact, you know, and what this just means is that b times the quotient plus the remainder will give you back your original number. Okay. So on the number line, obviously, just easily you can see if this is a, then you were just trying to see how many jumps of size b you need to make. Yeah. And let's say this, I mean, really be, let's say till here. And then this small thing is your remainder. And there are too many of these. Okay, so this is standard stuff. And this is introduced when you touch upon the notion of divisibility, or rather, whether two numbers can be divided when you are in natural numbers, and then we say no, and then we have this quotient remainder. Okay, so this is something that I assume. Now, let me ask a question. Okay, prove. Yeah, let's see. Prove that G.C.D of a comma b, because we will be asking a similar question in polynomials. So first we do this, try to do this. Prove that G.C.D of a comma b is equal to G.C.D of b comma G.C.D of b and r. Okay. Let's try this. Let me just check for a few numbers. Yeah, so we can just together check for a few numbers. So any two numbers anybody wants to say? Two numbers? Good. So if r is equal to 0, then what is the, so if r is equal to 0, then what is the GCD of a and b? Good. Does everybody see that? Yeah. So if 4, since 4 divides 8, we know that the GCD of 4 and 8 is equal to 4, right? The greatest common divisor is the divisor itself because one divides. Okay. What is the GCD of b and r? No, so it should not be 0. Yeah, so that can be. So what is the GCD of 2 and 0? So I am saying that it should be 2 because 2 divides 2, but 2 also divides 0. Now, why do we say 2 divides 0? Would anybody wants to explain this? It's just a logical point. Yeah, right? Because you can write 0 as a product of two numbers, of a number which of 2 and some other number. You can, and these are all integers. So I mean, we all just this is a fact, and it's obvious that any number divides 0. Any integer, those are the numbers for which it makes sense to ask what divides the other. And for those, 2 divides them, any number divides 0. So you see, when you ask this question, if R is 0, in fact, we have checked that this is true when R is 0. So the GCD is B. So it is true when R is 0. When R is 0, its result is true. Please interrupt me if there is anything that is not clear. So this is done. I was just going to write a few examples. Yes. So today what we are doing, we are going to be looking at, some GCD related questions in polynomials. Yeah, that will help us to answer many questions we'll see, even about divisibility and roots and so on. But for that, we're just exploring the divisibility of numbers for a minute. Then we go to polynomials. It will be an easier transition. So we just wanted to prove this fact. If you divide A by B, you get remainder, then the GCD is preserved. GCD of A and B is equal to GCD of B and R. This is the fundamental question. Now, for those who are thinking, if you just keep thinking, I'm just going to write an example. Maybe I'll just take 2. So you can check that it matches and take your own example and check that this fact matches. This fact is true. So any comments so far? If you try for these concrete examples, you see that this fact is true, but it may also remind you that you have used this fact somewhere else. Now, that I cannot guarantee, but you have used, but can you notice it? Especially when you take the concrete examples. Okay? Keep trying. Okay, so any comments? Yeah. Okay, let's see. What happens if I take r equal to 1? So this is done. In this case, can you please prove? Somebody please, if they understand how to prove this. If the GCD, so I mean, if the remainder is 1, then this is 1, no doubt. GCD of B and 1 is 1. Can you show? So now you need to show that the GCD of A and B is also 1. Right? Right. If the remainder is 1, then you want to show that the GCD of A and B is also 1. Can you show that from this equation? GCD of A and B what can it be? Let's say if D is the GCD, can you show it as 1? Come on, I've done this with some of you would know this and should be able to do this. If this is D, can you show that D is 1? Yes. Okay, so D has to divide BQ plus 1. Why? Because D divides A. Okay. Now, so why should D divide 1? No. But your reasoning is going, you know, I don't know. If it divides, you already sort of try to frame it. I mean, that's going in the right direction. Let me just frame it. So D divides A and D divides B. We know this. Yeah, so now it should be clear to you, right? That D has to divide. Others, can you reason it? I mean, yeah, Aparna, Ishana. Yes, yes, D divides B, right? So D has to divide 1 also. Yeah, D divides B, D divides BQ, right? But so D divides B, so D must divide 1, right? Because if it divides this and divides this, it has to divide the difference. So D divides. Okay, good. This is, I mean, this is the only way to do this. Right? D has to divide A and D divides. That's the definition of GCD, right? I mean, at least the common divisor. And then, so, I mean, for those who have done the number theory part a little bit, is this a new reasoning? No, right? It's just a similar thing, similar thing we have done earlier. Okay, I mean, is everybody following? Yeah, good. Yeah, because yeah, you two have done it. Yeah, Pragdish is also there. Maybe Satya is a little bit new, but it's you can see that the reasoning is this is the way you reason it in this case. And this is a standard because this is sort of the only way. There's not much to do here other than this. Okay. Now, how do you do it in general? If you don't make any assumptions on R, yeah, and that's homework. So the same thing, you have to take D as the GCD of A and B. So you say, okay, let D be the GCD, okay, of A and B, and then you assume this, and just like we have done, you show that D divides R. You show D divides 1, you same way you show D divides R, right? And then you show the reverse also. Okay. So let's leave this for homework. Now you have to think a little bit. Okay? Please try this. So it's like you take D to be the GCD and then you show D divides this because D divides R and B. You do the reverse way also. Get all right. So you work that out and you let me know if it's stuck. We will also revisit this in the next class. Maybe with some added. All right. So this we assume. Now, could anybody highlight the importance of this? Well, anyone? I mean, why is this? I mean, where do we use it? So now, just tell me if this is wrong. Most of you, I think all of you would have used the long division method to compute GCD, right? There is a certain long division method to come. Now you may call it different things, GCD, yeah, and it sort of maybe goes like this, right? So if you have something like any number, I don't know, 1002 maybe, yeah, 1002, and let's say you take something 30 maybe, right? If I ask you to calculate the GCD of this, obviously factorization is one method. You factor both the numbers into, but can anybody tell us what is the long division method to compute GCD? How would you use it in for these pair of numbers? You may call it a different thing. You can tell me what that is, but without factorizing the numbers, there is a way to find the GCD. If you have done it, then just tell me how you do. Right. So we begin to do that, and so then what do we do? Ah, okay. So right. So you take the quotient. So what is it? What is the quotient? So is it 12? Sorry, remainder is 12, right? Right, okay, right. So 990 and the remainder is 12. And then, as you said, we continue. So you continue the same process. Oh, so I just plug in the charger. So this method you guys are familiar with. Now, the question really is, why does this method return the correct? Yeah. I mean, apart from the numbers on which you have practiced, you can only practice finitely many numbers. Okay. Beyond that, why is it true? Why is it going to give the right answer for any pair of numbers? Because it is not the definition of GCD. GCD is a very strange thing, very different from GCD, right? Has anyone of you ever asked the question like why does this? So 24 and then 6 and I don't know 6 fully divides. So you stop. Yes. And then you say that because this fully divides 1002, this is much. But why is this a GCD? Well, in this case it works, but why will this always work? Why does the method work? Do you see the connection with what we have proved? Go on, go on. That is, yeah. So you write this in the form of this. Maybe this is the right B first. Yeah. So okay, you write this in the form of BQ plus R. Then and why is that correct to do? Because we have proved that the GCD does not change. Okay. So we set out to compute the GCD of 1002 and 30, But then we sort of apply the rule to a smaller pair of numbers, right? We apply the rule to a smaller pair of numbers, but that is not a problem because the GCD has not changed. Yeah, this is a fantastic, if you think about it, it's a very interesting idea, though maybe you have not thought about it before, maybe why it works. But if you think about it, it's a very interesting way in which this works, right? There is a certain preservation that is happening, and obviously the numbers are getting smaller, and they will get smaller because R is strictly less than B. In a sense, they're getting smaller, the pair of numbers, but you can understand. But the GCD is not changing. So if the method works for smaller, if it's true, if the method works for the smaller number, then it's true for these two larger pairs also, because the GCD has not. And obviously for smaller and smaller numbers, it's obviously easy to check that it is true. And eventually it comes down to one dividing the other, where it is obviously true that you pick the smaller number as a GCD. That is what we did in the beginning, R is equal to 0. Okay? But the point is that this thing that we did was essential, okay, to understand that this method is correct. This Euclidean algorithm, long division used to compute the GCD, does always work. Okay? So that's what we have proved. Now we would like to do this in the setting of polynomials. Okay. So so far, are there any questions? Okay. All right. So then we move to the setting of polynomials. So polynomials. Now, once again, if you have done long division in polynomials or not done, we'll see. The point is that given any two polynomials, px and 2x. Yeah. So right now I will not say the coefficients are in what, where, doesn't matter. For now it is just given any two it does matter, but for now it's just any two polynomials, px and qx. Let's assume that degree. So here degree would be the way to compare, right? Earlier it was just a number, but now we are looking at the degree. Degree of px is more than, or it could also be equal, not a problem. Degree of px is greater than equal to 2x. Yeah, we would like to say that again, that you could divide and you have a remainder. So there exists yeah, so maybe this is not such a good notation. You see, because the qx is used for quotient. There's no rule like that, but it just makes it easier to understand and so on, right? It's better to relate to. There exists, I'm just writing in small now, 2x and rx. So you can just see it's very similar to what you have done in case of integers. This is what you're dividing by, and you're getting a quotient, and you're getting a remainder. Is this fact correct? Yes. Right. So this is what really division means, right? The long division that you have is a way to actually find the answer, to find the answer easily, more easily than it would be if you did not have a set of steps that you follow. So now the question is, what can you say about the degree of the remainder? Yeah, is there anything that you can say about the degree of the remainder? So if you have done, you would have done exam. It will be at most the no, 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 no. QFX we cannot really say much about. Right? You can sort of understand that because, right? I mean, if you take some very big number, no, QFX, some very big, sorry, polynomial. QFX we cannot control, right? But you can say that it is less than the degree of what you're dividing by. So it is just very analogous to what you have for numbers. Right? Okay. Maybe to get a better feel for this, how about we do this? I give you two polynomials and you divide, let's together try to divide one by the other, get a remainder without using the Euclidean algorithm, without using that long division. Let's try to do it. Okay? Then we can understand why this really happens and holds true. You may already have some intuition of why this should be true, okay, and so on. But let's just take any two polynomials. It's slightly interesting enough so that it's slightly challenging. So maybe you could take x to the 5 plus 2x to the 4 minus 3x cubed, plus x plus 10. So this is your fx. Okay. And the gx maybe is different. Now, I have not asked a clear question, so we'll have to do this together and see what I'm trying to say. Yeah. What I'm trying to get at is trying to tell you that this thing that we write, that given fx and gx, you can get a qx and rx. This is sort of the final packaged result of something more fundamental. Okay? And let me just say one sentence before I try to start doing this is what the goal is that from fx, we are trying to take away chunks of gx, as many as we can, and then finally end up with a residue, a remainder. Okay? And this thing is the final packaged version of that after you do the process. So from fx, we try to take away chunks of gx. Okay, as many as we can, and then we cannot do, then stop. Okay. So, but still, I'll have to say more because I don't think it's much clear. But just that when I do it, you can sort of relate to it a little bit. So, what is the easiest chunk that I can take away? First of all, which is not the right way to sort of, it becomes longer if one does like that, but it's easier to notice that maybe this 3x squared chunk is there in front, right? There is a 13, but this chunk is something that can be forgotten if we are interested in the remainder, right? But we are, let's say, interested in the quotient also. So now we would adjust the polynomial. This is a chunk of x squared plus 1. Okay? But let's say we have to do a few more steps. So as to understand maybe what I'm trying to say, because it's just one way in which I do these things a little bit sometimes, and I found it being useful in many places. Also, obviously, to understand that this is a fundamental thing. This and let's try to take some other chunk. Maybe we can do this. So from this, so I could do it in a trick way, or I could do it in a, yeah, let me just do it in a trick way a little bit. Okay, so what I could write it as is, see, at no point am I really changing anything. Oh, what happened? Just stop. I'm not changing fx. This was fx, second thing is fx, third thing is also fx. It's just that it's now looks different. And so this 13 is writing it. You see why I did it, right? Just to take away one more, because this will now give me again x square plus 1 as a factor. Now this looks very strange and unorganized, which it is. But just that it's an attempt to show you that what this quotient remainder is trying to achieve. And sometimes these nuances are what we need. And we need parts of these sometimes are not the final result, and so on. Yes, I forgot the x. Good to notice that. Yeah, the x should be there. Yeah. Yeah, so the x I should write maybe earlier, but okay. So this is what we have so far. So now you can see this is again a chunk that will be like, that will come in the qx. The gx is the x square plus 1 times the qx would be. But now let us continue and see. Now really we have to focus on the x to the 5. So how should I manipulate the x to the 5 to pull out x square plus 1 as many as we can? Yeah. So, I mean, again, we could play some trick and do, but if we do this like rather directly, it is this, right? And then I could write, I just done a plus minus 1, right? This is all I've done, right? And then what it does is it gives me a minus x cubed, which is better than x to the 5, and it gives me one more chunk. Okay, don't use the word chunk if you're talking to some in an official place, maybe, unless you are. This is just what I'm saying. Okay, just away about this. This is yeah, and everything else just repeats. Okay, but let's just keep writing it because we're assuming we're doing this for the first time. And let's this x square plus 1. And now you see it sort of simplifies. So let me just write one more line. Point is, now you can see that this is the x square plus 1, and then there is x cube, and so there was more things, right? It's minus 3, which I didn't write there. Minus 3. So if you're getting slightly irritated, but you see, this is like really getting down and doing the thing. Okay. So we're going minus 3, and then it is minus 2x square, this one, right? So plus 2. What you see, now this penta is kind of, I've bought a new one, but I don't know where it is. We kept it. Find it. Okay, I didn't buy, I got it. Anyway, this thing, and this will be plus. Okay, and then I just simplify it. At no point have we changed polynomial. That's the best part. So minus 2x square. So that's plus 2 minus 3. Now you have to work on this and similarly simplify, and this is not going to be difficult, right? So you have minus this, and you have the x. Oh yeah, how did I write minus? Because here it was plus. Yeah, good. So then it's all more strong, right? So it's -5 or something, right? Thank you. So then it is x square. Again, you do the same thing, okay? Minus x, and obviously there is this other part which is kind of, we cannot take any chunks, right? This is what we write, and again you copy this. Just copy this thing and you copy this thing, right? And as you do it, you will see that again you get one more chunk, right? This basically this will be the total chunk of x square plus 1 is x square plus 1, and this is the remainder. Yeah, minus x. No, this is the quotient, sorry. And the remainder is the residue, the part, this part, and this part, right? So it turns out to be only 15. The next gets cancelled. Okay. So what have I done? I have written, I made a mess, but I've written this thing. Uh, this was the original polynomial, out of the original polynomial. I've written this polynomial by just taking away pieces of x squared plus 1 as much as I could, yeah, in this form. And so this is your quotient, this is what you're dividing by, and this is dividing. This is what you would get if you try to do it by long division, unless there's some silly mistakes I've made. Hopefully not. I mean, this should throw some insight into, really why do we always get there? So you can kind of now feel, right, that given anything else in place of that fx, you, without using the long division, can actually find the quotient. Because the long division, I mean, how do you know the long division is correct? Right? It's a method, and then it's a very good method and so on, which you did not invent, right? And first of all, why does it work? But even if you can answer this still tells you that it's a very fundamental thing. At each stage, you're just trying to take away as many, multiples of x squared plus 1, and writing the final. So is it any good? Any? Okay. All right. So from here, we have sort of proved this. I mean, one official outcome is that we have proved this. You can extend the same method and prove it for any fx. You can use induction, because at 8th stage, I'm sort of reducing the degree. You should start with x to the 5 and sort of reduce the degree by the trick I did in the third step. You do that in the first step. You reduce the degree and you say, well, yeah, I've reduced the degree now, smaller degree by induction, it's possible. The higher degree I've reduced to smaller degree, so it's possible. Okay. So you sort of fix the degree of gx and you do the induction on the degree of fx. And you can prove that this works out. But that is a formalism. This method that I've shown you, you can see it's very primitive, right? It takes a lot of steps, but there's nothing not to understand. It tells you that, yeah, this can always be done. Okay. No matter what this was, if this was 100, then what would I have done? I would have taken 98, and then I would written the x square as plus minus, and then I would get this x square plus 1 times x to the 98 and an extra x to the power 9. Now I need to reduce this, but that is reduced, so I can further reduce by an inductive. By the same way, I can reduce further. So it's a completely elementary thing. Okay. So any questions? You can take a pair of polynomials for yourself and try it later, and then try the long division and check that they both. This has several advantages, but we will see that in the right context when they naturally come. So if there are no questions, then this is what we have so far. Now I would like to get more into this. Yeah. Yes, that is correct. Yeah, so that's another thing maybe that I should just write here. So I'll just write that, yes. Otherwise, the degrees on both sides will not be equal. Right? So to make the degrees on both sides equal, you will need that degree of qx adds up to good. So that's certainly true. And that's another piece of check use. Sorry. So this is okay. Now, yeah, so this is a thing, a degree of this times degree of this. Now, this is again just obvious thing, right? Because this degree is smaller, right? So the responsibility is on these two to make up that highest degree. And so the degrees add when you multiply the polynomials, you can understand that degree. Okay. So now I would like to ask a question, which I did not ask in the number case, okay? Because otherwise we'll spend all the time there. So show. Now again, this is just the theoretical questions. I mean, today's class is a little theoretical. So we have worked out a few things, but show that qx, show that qx and rx are unique. So maybe let me say, so unique means that there is only one such qx that you can possibly find. And the process I did, that by no means is telling you that it's unique. It could give some intuition in the sense, it's unique in the sense that you are taking as much as you can and then you stop at the extreme. And so there cannot be two ways to stop in some sense. But still one needs to prove that there is a unique quotient and then a unique remainder. So, I mean, how do you show that something is unique? There is no way to arrive at it directly, right? So you assume that it is not unique, right? So you assume that there is another uniqueness. Uniqueness is very important. You assume that there is another quotient, some other q, maybe q1x, and some other remainder. And now what should we do? So we have done this sort of, there's some other solution, and so let's see a uniqueness. So how do we now say that? How do we use this? So we have one solution, I mean one quotient and remainder. So the one of them is here, and then the same polynomial and same divisor, call it gx, same fx and gx, we're getting another equation. So why is this so a contradiction? Or why do we get that this and this are equal? Okay. And also Rx. We would want to say that it's unique. Yeah. So you may not know how to show this, but when you see two equations like this, what seems to be a natural thing to do next is to subtract. Right? You may not know how to get to the proof, but the natural thing is seeing these two equations to subtract. Right? So then what do we get? If you subtract them, so let's just first equate them, or whatever you call it. We equate them. And see, this is the natural thing to do. you have done this kind of thing earlier also. This is the thing. So all the time you would not know really how to get to the goal, but you should see from where you are what are the natural things to do, things to try. This, and again when you see this, again it's just natural to take this gx common. Now what can we say? It's a little abstract. So these are all just polynomials. I'm not giving you a specific polynomial, but we're trying to use small properties like the remainder is less than the remainder of Rx, the degree of Rx is less than degree of Gx, and so on to get some sort of to get somewhere, right? So this degree of R1x is also strictly less than degree of Gx. That's also true. Yeah. Now, from this equation, what can we say? It looks incorrect in some sense, right? The degrees. Look at the degrees on both sides. Yes, that's right. Yeah. So basically, this degree is less than the degree of Gx, right? Because the degree of Rx is less than degree of Gx. Yeah. Degree of R1x is also less than degree of Gx. When you subtract, the degrees cannot increase. It may not decrease, but it cannot increase. Right? So, I mean, this degree is less than the degree of Gx. And then you have another polynomial that you're multiplying it by. So the degree on the left hand side might even increase. Okay? So it can never be equal. If the degrees are not equal, there is no way the polynomials can be equal. Unless something is zero. The only way in which this can happen is zero is always there, right? If this is zero, that is the only way. This is zero, and hence this is zero. And that's what we want to show, that qx is equal to q1. That's the only way in which these two sides can be equal, right? If both are zero, that's it. That can happen. Not the degrees, but the exact polynomials. No, this exact thing is zero. That is the only way the degrees can start matching. So then that means that the qx is equal to q1x. They are matching in every sense, and the remainders are also then. So it's a simple proof. I mean, it's nothing to kind of just natural things to do. So you can see that this uniqueness is coming from the fact that the remainder degree is less, and that basically means that I was saying that you sort of pulled out as many chunks as you could, and so you get the, and that's why. So this is general principle in showing uniqueness. Okay. So far we are here. Now we know that this is things. Yeah. Now we would like to get into, so this I'll just remove this and here, and also unique. I'll just write it. Finally, the statement is this. There exists unique. Yeah. So the plan is from here to explain, to do a few things, and then explain why the method of finding GCD by long division works. Okay, because that's something that we obviously along the way you see we are learning these techniques, reasoning, this, that, and so on. This executing the so on, the long division without actually doing the long division, finding the quotient. But the general goal from here is to basically to show that why the long division is correct when it finds the GCD. Yeah. explaining the long division method of finding the GCD. I mean, there's a reason why I'm doing this, but explaining the long division method of finding of two polynomials. Okay, so that's what we want to do, and the screen has sort of so this Google Meet is working. Okay, now this is also right. So we will want to explain the long division method of finding the GCD of two polynomials. And then the next thing would be to apply that in problem. We'll come to that. But I would not want to do this today. Maybe think about it. What I can ask you to do, which will really do the problem, if you can do this, is GCD is just the analogous thing. You can even ask this question naturally to yourself. GCD of this is equal to GCD of Gx and Rx. This is what you would have to show. Yeah, it's similar to what we have done today. But maybe I don't expect that you are as comfortable with what is GCD of polynomials, yeah, as you might be with other, as GCD of numbers. So that's why I would spend a. Oh my, I hope everything was okay. Screen just went somewhere. I don't know what. So I pressed that task manager and got opened. No, so yeah. So we will just spend a bit of time, maybe next day or today also a little bit, into just understanding what GCD of two polynomials mean. It obviously means a common factor, and one can define it and so on. But we'll define and we'll also do a few how it is different from roots. Finding how showing that two polynomials have a common factor as a polynomial. What does it mean factor? It's different from roots all the time, and that's why this method is more. It's better at it's more general in understanding polynomials than roots are. The roots we cannot always find. The factors may be simple. We'll speak on all that next time and problems. But maybe I would like to end today with a problem which is has a flavor with what we did yesterday for those who were there. But you'll see it will apply to all of us. It's interesting. Maybe this is 100 to the 4. Okay, number theory. So guys are all yeah, we have all done that earlier. Is 100 to the 4 plus no 4 is 99 to the 4 plus 4 times 100 to the 4 prime. And yes, we will, as you can say, we'll use polynomials. Yeah. So think about this. I'll be back in a few minutes. Just think. See if you can tell me. So anyone has ideas? This will help give us an understanding in factors and polynomials. Let's see. So any ideas? Whether this could be okay. How about this? I mean, if I remove this, is this a prime? Now, if you are doing polynomials, then what's the natural polynomial to consider? Any natural number to the power 4? Sum is always prime. Sorry? Sorry. Prime, or did you say prime? Hello? Okay. So you took numbers like this. Okay. So that's different from the question slightly, but you will not always get prime. So that's another thing. Like last time you were doing the a square plus b square, yeah, in the Pythagorean triplets class. It's not always prime. So the fundamental reason why I'm saying this is because the primes don't have that sort of a pattern, right? I mean, you cannot write an expression and always prime. No. In fact, we'll prove later that no polynomial can ever be prime at all. Either ways, uh, no. So that is not correct. That is always prime. Maybe yes. Small example if you do, because initially there are a lot of primes. So the point is that what's the natural polynomial to consider here? Anyone? This should not be difficult. It should be this. I mean, there is simply no other. This is the natural polynomial to consider. Right. I mean, the 99 doesn't seem to be okay. It might be special, but oh, you have found that. Yeah. So why? Okay. So you have found very good, very good. You have found a factor. That's very good. You have found so mod 5 and by last digit method. Yeah, that's certainly very reasonable. That's correct. So maybe I'll just change it. So if I change this to 7, right? No. Then also last digit is 1, right? I mean, just change it to something so that the last digit is not. Maybe I don't know. Odd is odd 1, 3. I'm trying to say that we will have to use some other methods. So yeah, 5 is just 5. Yeah, let's say this one. That's the but yeah, that's so this is the thing. Either has to, there can be alternative ways. So that is working. But now for this again, you may find some other factor. You may find 7 or something as a factor. So that's can work, And so go for it. Try. But by the approach of polynomials, which is the general method, because if you give you very, very large number and large digit doesn't match, so this. Now the homework is to factorize this polynomial. Try to factorize this. If you can factorize this polynomial, then you will have a good chance of showing that that number can also be factorized. Right? And factorizing this polynomial, you can use the basic principles of a difference of squares, completing a square, and whatnot. Right. And then, so once you factorize the polynomial, then we'll talk about it will be a situation where you factorize it, but you have not found the roots, but still factorize it. You'll see. So try. This is also standard factorization. You will find this in NCERT books, I think, class 10. Either ways. So try this. Then you can try to solve this problem. So basically, I'm trying to say that for any n, 10 to the 4 plus 4 is not SIN. So this is the thing. So you factorize and Yesterday's class also, I mean, that was the induction class that we ended up doing a little bit of number theory. The end of how we showed how, factorizing the